So we go back and take a look at diffraction and interference of light. We also call that Young's double slit experiment, the experiment that was performed by a guy named Thomas Young. Discovered that, in fact, light does undergo diffraction and light does undergo interference, the same as any other wave does, lending more support to the wave theory of light. Young discovered that when light goes through these two openings, of course, it's going to diffract through both of them. And of course, when we get a crest hitting a crest or a trough hitting a trough, we get constructive interference. When a crest hits a trough, we get destructive interference. Now, we can't see that constructive and destructive interference like we can in water waves. If it was water waves, right, we'd see this, and we'd see those areas where the waves hit each other and interfere with each other. Because it's light, and you're not going to see the light unless it's reflecting off of something, we're not going to see it in between the screen and the openings here. But we can see it on the screens because it is going to reflect off of the screens. That is where we have constructive interference. In the middle, we have constructive interference. Crests hit crests, troughs hit troughs. We get bigger crests and bigger troughs, constructive interference. What we end up seeing on the screen is a bright spot. We also call that a maximum. We also call that an antinode. Right beside that, we get an area of destructive interference, which is going to be a dark spot right here, a dark spot, or a node, or we can call it a minimum. Right beside that, a bright spot, dark spot, bright spot, dark spot, bright spot, and so on. On the other side, the same thing. Dark spot, bright spot, dark spot, bright spot, dark spot, bright spot, and so on, and so on. Now, there's two equations that describe what happens here. There's the first one that you see up here, which is valid in all situations, and then the second one, which is valid in most of the situations. Let's take a look at what each of these variables mean, and then we'll discuss again why that second one isn't always valid and when it's not valid. Let's look at the letter D, the symbol D here. D represents the distance between the openings. And we're going to want to put that in, normally at least, we're going to want to put that in meters. It's going to be a small, small distance. Okay, if you get a really, really small distance, that's probably what it is little d. L represents the distance from the openings to the screen. That's going to be a bit bigger of a distance. It doesn't have to be a huge one. Okay, it can be in the range of meters, but it could also be smaller than that as well. It's going to be bigger than little d, though. X, this is the tricky one. X is what? Do you guys remember from last week? Last Wednesday and Thursday what X means? Travis? Yes. Yeah, it sounds silly, but he said, Travis just said, it's a distance between one of the red spots and one of the other red spots or something. Yeah, that's exactly what it is. It's between any bright spot and any other bright spot, or any dark spot and any other dark spot, or any bright spot or any dark spot. So in other words, it's any distance we want up here. It can be this distance. It can be this distance. It can be this distance. So how exactly do we reconcile that? How do we say that we can make X whatever we want and then still all expect to get the same answers? Good. N has to be consistent with it. So we know what X is, we know what D is, we know what L is. We have to recognize now that N has to be consistent with it. Now let's label our maxima. We're going to call this our central maximum. This is going to be our first order maximum, second, third order maximum. Same on the other side, first, second, third order maximum. If we're going with this first X here, from 0 to 3, what would N have to be in order to be consistent with that? N would be equal to what here? N would be equal to 3, right? 3 minus 0 is 3. What about this one? When we're going from 2 to 3, N would be equal to what? 1. 3 minus 2 is 1. What about this one when we're going from 1 on one side to the second order minimum on the other side? What would N be in that case? 2.5. You could say it's 1 minus negative 1.5, or you could say it's 1.5 minus negative 1. Okay, in any way you look at it, you're going to get an N equal to 2.5 there. Why the 1.5 here? Why did I say 1 minus 1.5? It's a dark spot, right? It's halfway in between the first maximum and the second maximum. So we're going to call that a 0.5. That make sense? So we got to be consistent, right? We got to be consistent. That's the big thing there. Theta. Theta is kind of like x in that it can be measured just about wherever you want, but it's not quite as versatile as x is. It can't be wherever you want. Okay, there's one kind of limit to that. It has to be measured from the central maximum. So it's the angle that's measured from the central maximum to any other maximum or any minimum. So it can be measured here, or it can be measured here, anywhere, from the central maximum to any other maximum or minimum. But n has to be consistent with it again. What's n going to be in this case when we're going from 0 to 2? 2 minus 0 is 2. What's n going to be in this case when we're going from 0 to the first order minimum? N would be 0.5, right? N would be 0.5. Okay, that's not all that hard. Just like when we were dealing with lenses and mirrors, though, we circled convex or concave, converging or diverging, because we didn't want to mix up a negative value, right? Okay, that was important because it was easy to mix up the focal length, right, of a diverging lens to make it a positive value if we didn't draw attention to that. It's really important here in these questions that you draw attention to whether you're dealing with maxima or minima. Because if you're dealing with maxima, it's all whole numbers, right? If you're dealing with minima, you got to all start adding the 0.5s. It's so easy to see a question that says, blah, 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 the third order minimum. What are we going to say? 3. Well, it shouldn't be 3. It should be, if we're talking about the third order minima, it should be 2.5, right? It's so easy to make that mistake. So especially if you see a minimum, circle it, draw attention to it so that you don't make that mistake. All right. We also said that this equation is valid all of the time, no matter what, as long as you're measuring the angle from the central maximum to some other maximum or minimum. The second equation isn't always valid. It's an approximation, but it's a very good approximation. It's a very good approximation for 95% of the problems that we'll see. But there is potentially the odd question where it's not a good approximation. Here's the rule. If the angle is above about 10 degrees, then that equation is no longer valid. If the angle is above 10 degrees, this equation is no longer valid. But you know what? I don't want to figure out the angle every time. We could, but I don't want to do that. If we're given a question where we're told the angle is 17 degrees, all right, easy. Just don't do it, right? But if we're not told what the angle is, how do we know if this is going to be a valid equation? Here's the rule of thumb. It's not the rule, it's the rule of thumb. In other words, this is what we're going to use, even though it's technically not the rule, just because it's a lot easier, that's all. We're going to look at the values of L and X. L and X. If L is greater than 10 times X, we're going to use that equation. That is, if it seems to be applicable, right? If the other one's the one that fits the givens that you have the angle and it's 6 degrees, and you know that this equation is valid, but you have the givens for this one, then just go ahead and use this one. But if you have what seems to fit this one, you got to do that check. Is L greater than 10 times X? If it is, you're good to go. If it isn't, then there's something else you got to do. Now, what do you do if L is not greater than 10 times X? Well, we got to go back to this equation, right? We got to go back to this one. Well, how do we do that? If we have an L here, and we have an X, and L is not greater than 10 times X, then get the angle. How do you get the angle? As long as you're measuring from the central maximum, the angle can be found by saying tan theta is equal to opposite X over adjacent L. So you can get theta. You can get that every time. I'm just saying, look, it's easier to do a quick comparison of L and X than it is to find the angle every single time to ensure that you're under 10 degrees. Make sense? Now, the reality is the number isn't exactly 10 times. You could get away with going slightly more than that. Okay, we're being a little bit conservative on that one. Okay, but it's a nice, easy number to look at. Okay, you can tell most times without even punching it into your calculator that L is greater than 10 times X. Right? All right, we had some questions that you worked on last Wednesday on page 689. Any issues with those questions on page 689, please? Okay, let's take a look at number 3 then. It says the second nodal line. You know what I find useful sometimes with these questions? Draw it out. You get confused as to what the second nodal line is. Draw it out. Here's my screen. Okay, here's my central maximum, my central bright spot. Okay, this is my first bright spot, my second bright spot, my first antinode, my second antinode. If we're talking about the second node, then we're talking about this one right here. It's 0.095 degrees relative to the central antinode. All right, so we're going from the central to the second node. We're going from 0 to 1.5. What's n going to be there? What's 1.5 minus 0? 1.5. So n is going to be 1.5. Theta is 0.095 degrees. Now that's a tiny, tiny angle, right? That means that either of those equations would be applicable here, right? But listen, if you've got the angle, why would you try to use the one without the angle, even though it is valid in this situation? We got something at 0.4 millimeters. What is that? D, little d, yeah. I'm going to actually make it 0.4 times 10 to the minus 3 meters. That's not scientific notation, right? Scientific notation would be 4.0 times 10 to the minus 4 meters. But why bother going one extra step and making a mistake with that? Right? If we know it's 0.4 millimeters, tack on a 10 to the minus 3 on the end of it, then we don't have to worry about moving the decimal place and one more possibility of a mistake. We want to find the wavelength and the color. We're not going to panic so much about the color. We do want to determine whether it's visible light or ultraviolet, okay, but we're not going to worry so much whether it's violet or indigo, okay? Okay, we're going to say lambda here is equal to d sine theta over n. D with 0.4 times 10 to the minus 3 times sine 0.095 over n, which was 1.5. When we solve for lambda there, I think we should get 4.4 times 10 to the minus 7 meters. Make sense? How do you determine what kind of EMR it is? Well, let's get the frequency from that. F is equal to V over lambda. V is 3 times 10 to the 8. Lambda is 4.4 times 10 to the minus 7. Does anybody have the value for the frequency there? .81 times 10 to the 14 hertz. All right, that's within the range of visible light, and it's clearly in the upper range of visible light. I don't think you'll ever be asked a question where you have to identify the exact color, but if you are, then the options for this one might have been red, orange, green. So red, orange, green, and violet. Well, look, the range of visible light is 4 to 7.5 times 10 to the 14. Which does this look like? 6.8. It's a lot closer to 7.5, right? So what's it going to be? Red, orange, green, or violet? It's going to be violet, right? If you ever have to find the color, specific color, then it'll be pretty clear to you if you use this logic. You're not going to get the option of indigo and violet. Honestly, you get indigo and violet, I couldn't answer that question. Okay, if they gave me the choice of whether this was indigo or violet, I wouldn't know the answer to that question. Okay, but I do know that it's not green or orange or red, right? Because it's so far up on the spectrum. Okay, second set of questions we had were on 691. Okay, let's take a look at number 2. Monochromatic light. We're using monochromatic light, one color light, right? What we see when we use one color light is exactly what I showed you. Call this our central maximum, first order bright spot, second order bright spot, and so on, right? And the same thing on the other side. If we were using, oops, that should be a 1. If we're using polychromatic light, more than one color, what would we see? We'd see this. But we'd see another one for orange. and another one for yellow, and another one for whatever colors we were using, we'd see an interference pattern, a separate interference pattern for each of them. Let's say we're using two colors. Okay, two colors, red and violet. What would we see exactly? Well, we'd see a central bright spot that consists of red and violet combined. Let's just say yellow, okay? Okay, it's white light, or it's red and violet combined. What would we see next to it? We'd see all the violet bright spots. Then what would we see? Well, we'd see all the red bright spots. And if we had orange, we'd see all the orange bright spots. And if we had green, we'd see all the green bright spots. What's the difference here, really? None, except you've got multiple spectra. Multiple spectra, right? If we've got one color, we've got one spectrum. If we've got multiple colors, we've got multiple patterns there. Now, what if you ever do see that? What if you ever do see a question with polychromatic light there? What should we do? Pick one. Pick one. If you have data for red, then ignore the blue. Pretend it's not there. Even if it is there. Whoops. Even if it is there, pretend the blue's not there. That makes sense? If you have data for blue, pretend the red's not there. One quick little thing, though. A prism breaks up light, right? A prism splits up light by refraction. A diffraction grating splits up light by diffraction, by interference. What do you notice about the biggest difference between the pattern that a prism produces versus the pattern that a diffraction grating produces? Besides the fact that in a prism, you get one spectrum, right? Red, orange, yellow, green, blue, indigo, and violet. Done. One spectrum on the screen. And here you get 1, 2, 3, 4, 5. You get a whole bunch of them, right? Besides the fact that you get a whole bunch of different spectra, what do you notice about the difference here? A prism goes in what order? Red, orange, yellow, green, blue, indigo, and violet. The pattern produced by diffraction grating goes violet, indigo, blue, goes backwards, right? Does that make sense? So it looks more or less the same, except it goes backwards. And there's a lot more of them, right? It's not one pattern, it's multiple patterns. Okay, so we are dealing with monochromatic light here. We don't have to worry about any of this. But even if we did, listen, all you got to do if you're dealing with multiple colors is pick a color. Pick a color and treat it as a monochromatic problem, okay? Don't get bogged down by having 4 or 5 different colors. We got D here is 3.00 times 10 to the minus 5 meters. The distance between antinodes, that's going to be 3.10 times 10 to the minus 2. Now, it doesn't say, it should say between adjacent antinodes. That would make n equal to 1. L is 1.5, the distance from the screen to the openings. Let's get the wavelength there. Clearly, this is the one that we would want to use, xd over n times L, but can we? Can we use it? Is L more than 10 times x? Is L more than 10 times x? Yes, it is. Okay, so this is good. If it wasn't, then all we do is find the angle and go from there. Okay? It's very rare that you have to do that, but I have seen that probably a couple of times on a diploma exam over the years where we've had to actually find the angle because the angle is too big to use that second equation. It's not very common though. All right, x is 3.1 times 10 to the minus 2. D is 3.0 times 10 to the minus 5. N is 1, and L is 1.5. When we do that, I assume we get 6.20 times 10 to the minus 7 meters. F is equal to V over lambda. What does that work out to be for frequency? 4.8 times 10 to the 14. All right. If you asked me to distinguish that between red and orange, I'd have some trouble with that. If you asked me to distinguish that between red and green, it wouldn't be any problem at all, right? It's really close to the end of the spectrum, to the red end of the spectrum. So you know it's going to be in that red-orange range somewhere. All right? Finally, the last set of questions involved diffraction gratings as opposed to just two openings, where we had, instead of this, with two openings, 1, 2, we had 1,000 openings, or 2,000 or 3,000 openings per centimeter, which seemed to complicate things a lot, but it doesn't really have to. In the end, if we have this many lines per centimeter, or this many openings per centimeter, that's the inverse of the distance between the slits. So if we have 2,500 lines per centimeter, we don't have D, but we do have 1 over D. So all we have to do is flip that over. All we have to do is flip that over to get the value of D. 2,500, x to the minus 1, 4.0 times 10 to the minus 4. Well, now the question is just like any other question, right? We know what the value of D is. In centimeters, we want to convert that to meters. Just do what you did for the rest of them here. What else do we have in question number 1? The distance between the central antinode and the third dark node. Central antinode, first, second, third dark node, what's that going to be? 2.5. So n would be 2.5 there. We're going to say x is 20 centimeters. We're going to say that's 0.20 meters. L is 0.5 meters. Let's make this divide by 100 to get meters for a little d. And let's solve for lambda there. Lambda is equal to xd over n times L, right? Can we use that? Wait a sec, we can't? Why not? Good, good. We can't use that equation this time because L is not 10 times greater than x. Does that make sense? So we can't use it. So what do we got to do? We got to get that angle. Okay, our value for x is 0.20 meters. Our value for L is 0.50. Solve for theta, we're going to say it's the inverse tan function of opposite over adjacent, 0.2 over 0.5. Does anybody have that angle there? Sorry? 21.8 degrees. Thank you. So clearly that's bigger than 10 degrees, right? That's way bigger than the angle that we want to max out at. So let's go to our other equation. Let's go lambda is equal to d sine theta over n. 4 times 10 to the minus 6 times sine 21.8 over n of 2.5. What do we get for lambda there? Thank you. 5.94 times 10 to the minus 7 meters. So the answer in the book was wrong for this. What do you think they did? They just went lambda is equal to xd over n times L, right? So they overlooked that. Okay? Listen, they're not the first people. They won't be the last to do that, right? I've done that. Yeah, I've missed that before. Hopefully you, if you're going to miss that, hopefully you miss it on practice questions, not on a diploma exam. Okay? Be careful. Okay? When you want to use that other equation, xd over n times L, when you want to use that, always do your check. Always do your check. Now, odds are it's going to work out for you. 95% of the time it's going to work out for you anyways, even if you forget to do your check. But that other 5%, we end up getting a wrong answer like the people that wrote the textbook did for this question. All right? Any other issues there? 1, 2, or 3? Sorry, one more little thing that I wanted to point out here, guys. If you're doing a conversion in these questions between centimeters and meters or millimeters and meters, make sure the centimeters is on the top. So if you've got 2,500 lines per centimeter, don't try to convert that to lines per meter. Don't do that. Okay? Get it in D first. Don't ever try to convert 1 over D to meters. Get D and then convert it. Make sure the centimeters, the meters, whatever is on the top. Make sense? How do you convert centimeters to meters? Divide by 100, right? How do you convert lines per centimeter to lines per meter? We have to times it by 100, and that's confusing, right? Because everybody always thinks centimeters to meters is divide by 100. But when it's on the bottom, it's not divide by 100, it's times by 100. So just get it on the top. Just get D, and then do the conversion the way that we always do.